Swayam Prabha. Digital India. Educated India.
Welcome. Last time we were discussing about the Maurice-Lécar equations, and we briefly introduced to the idea of what a solution of differential equations like the Maurice-Lécar equations would mean if we were to plot them, that is their functions of time from a particular initial condition on a plane where we plot one state variable versus the other. So, as we have introduced the Maurice-Lécar equations, so if you recall, it is given by the C dV dt equals I external minus m infinity v, this is for the calcium channel, minus v minus E calcium minus W times V minus E k minus this W will have a G k bar, which is the overall, and here there will be a G calcium bar over all conductance of the entire neuron, and G leak into V minus E leak. And the only other dynamics is for the W, which is the same as the Hodgkin-Huxley gating variables, that is dW dt equals W infinity V minus W by tau W V. So, we have the explicit functional forms of W infinity V and tau W V, and we are saying that, let us say, if we start the system at V 0 and W 0, then how the system will evolve in time, or basically the solution to this set of differential equations can be plotted as let us say either V as a function of W or W as a function of V for the different time points that we are considering. And this plane that we have is what is called the phase plane. That is, if we have a V on this axis, this is the membrane potential, and W on this axis, W varies from 0 to 1 being a probability, and V varies in the range of the voltages that are involved in neuron. It depends on the kinds of ions that are there, and in this case it will be maybe around minus 90 millivolts or minus 80 millivolts to around plus 140 millivolts. That is the calcium reversal potential and the potassium reversal potential in this case. And what essentially we said is that dV dt at a particular point, let us say it is V 0 W 0, and dW dt at that same point V 0 W 0 represent the rate at which each of the state variables are changing with time at that location V 0 W 0. So, if this is V 0 and this is W 0, let us say, then here we have the V 0 W 0 point, we have a particular value of dV dt, which means that the voltage is changing at that particular rate. That means, if the system were here, that is this system that is described by these set of differential equations, then the system will try to change the voltage according to dV dt. So, essentially that it will point in that direction if it is positive, and the opposite direction if it is negative. Similarly, we have dw dt, positive if negative, then on this direction, and the resultant is the direction in which the system will go. And we mentioned that if we can grid, if we get the entire phase plane to have a grid like points, and for each point if we calculate the dv dt and dw dt and plot the corresponding arrows, then we will be able to get an idea of how the system would behave in the different parts of the phase plane. So, that is the very basic idea here. However, I mean, to actually to look into the phase plane, there are a number of tools that are available that will help us in understanding the system in much more detail and inferring properties about the system in much more detail. And that constitutes what we will call the phase plane analysis, which we will be doing for MLE and Hodgkin-Huxley reduced systems. So, in order to go forward, let us talk a little bit about what more can the phase plane give us, what methods can be applied in this plane of the two state variables that we are talking about. So, first of all, other than the net direction along which the voltage and W, or rather the whole system, will be going at each point, let us say that if we are at one particular point, then is it possible for the system to be moving in two directions? That is, from this same V0 and W0, can the system have two arrows as possible solutions? So, the answer is no, and that follows from the existence and uniqueness theorem. Existence and uniqueness theorem for the kind of system of differential equations that we are talking about, the system of ordinary differential equations that are coupled through the state variables. It says that if the derivatives, that is in this case dv dt and dw dt, are exist and are continuous throughout the phase plane or over whatever region of the phase plane, then at a particular point, if that is the initial value, then there is only one possible direction in which the system will go. That is, the direction of the trajectory from that point is unique. It exists and is unique. So, we will not go into the proof of this. There is a formal proof of it. We will just assume it and go forward. So, this has a very important implication in the phase plane. That is, if you ask now yourself the question that can at a particular point, can two trajectories cross each other? So, let us say I had started the system at this particular initial condition of V1 and W1, and this is V2 and W2. So, just applying the theorem that we learned, if we consider I'm sorry, this is V2 and W2, this is V2, and this is the intersection point, assumed intersection point. Now, if you ask the question, if this is, let us say Vi and Wi here, then if we started the system at Vi and Wi, Wi as the initial point, then there must be two solutions at that point. That is, the system will be going in two different directions at that point, which violates the existence and uniqueness theorem. So, the conclusion is that trajectories do not intersect each other. What we mean by trajectories? Trajectories, as we had mentioned, are simply solutions of the differential equations, set of differential equations that we are analyzing in this phase plane. And the Vt Wt curve is the trajectory if we start from one particular initial condition. So, that is one aspect of it. The second part of this idea is that of the phase plane is that let us say we have this as the phase plane V and W. Now, let us consider our system of differential equations dV dt equals some function of V and W. Let us make it V1 F1 and dW dt is F2 V comma W. So, the line along which, or the curve, or the whole region, or the points along which in this phase plane there is no movement of V. That is, if the system is put in those points, then there will be no change in V. That is described by the point that sets this dV dt equal to 0, or rather for dV dt equal to 0. So, for dV dt equal to 0, we need the F1 V W equal to 0, and so this essentially is an equation, a relation between V and W, and that will be a curve in this phase plane. So, if you think about our similarly, if we think about this dW dt equals to 0, that means that F2 V comma W is equal to 0, and that would be another curve in this phase plane. The point here is that along these curves V does not change, or rather along any points on this curve V will not change, and along any points on the next curve, that is F2 V comma W is equal to 0, W will not change. That is, if the system is put there, then there is no net change in W. So, arbitrarily, if we think that let us say this is sort of the regions along which the combination of V and W values that come up for F1 V comma W equals 0, or in this case it is F2 V comma W equals 0, then at this point, if the system is there, then there is no net flow along the V direction, that is in the horizontal direction, which means if we have a trajectory crossing this line, it must cross it vertically. That is, the direction of flow must be either in the upwards direction or in the downwards direction at that particular point. And similarly, on the other curve, it is the flow must be along the horizontal direction, because our dW dt is 0, that is, there is no net movement at that particular point along the W axis. So, the points along this whole line are going to behave in the same way. That is, anywhere the trajectory crosses this line, it is going to this particular line, that is the F1 VW equals 0 line, then it will cross vertically anywhere along there, be it here, be it here, be it here, anywhere. Similarly, anywhere along this line, it has to be horizontally crossing them, the trajectories. So, these lines are called the null lines, that is, this particular one would be called the V null line, and this particular one will be the W nullcline. Or if it is the variable state variables are x and y, then x nullcline, y nullcline, or whatever the variables are. So, now we are posed with an interesting situation, that is at this intersection of these nullclines. So, at that particular point there is no net flow along V or along W, that is both dV dt and dW dt are 0 at this point. So, this point is such that dV dt equals 0 and dW dt equals 0. So, ask yourself, if I put the system exactly at that intersection point, what would happen? So, obviously the answer is that it will stay there forever, because unless we get some perturbation, the system is not going to move in V or W ever from that particular point. And these points are called equilibrium points or fixed points or stationary points. There are a number of ways in which people call it. We will mostly refer to them with these two ways. So, now let us go forward exactly as to how the MLE nullclines are, and try to see a few things, that is this is V and W. Then from our equations that we had from these equations, that is the C dV dt and dW dt, just recollect that. And if we set, let us say, dW dt equals 0, that means this is equal to our W infinity V minus W divided by tau W V. So, we have a relation between W and V, that is, if this is 0, we have W equals to W infinity V as the solution to this equation, and we will call this the W as the W nullcline. So, these are the W's along which the dW dt is 0. So, and you remember that we had the W infinity V also defined as our half into 1 plus cos hyperbolic V minus V3 by V4, and our V3, V4 are already supplied to us. These parameters are known, experimentally determined, and then empirical, a functional form is derived with fitting, then we get the parameter values. So, with this W infinity V's, this is, as you can see, it is a relationship between a W and a V. So, this is our W nullcline is going to be this half of 1 plus cos hyperbolic V minus V3 by V4. So, that means W as a function of V. So, this will turn out to be something like a sigmoidal curve, and then it will go saturate at 1. We are drawing, let us say, only the bottom half of it, let us say. And similarly, if you now remember the dV dt line, then if we set the dV dt equal to 0, then we have this I external, let us say there is no current. So, this is also 0 minus our G calcium bar M infinity V, V minus E N A minus gk bar w v minus ek minus g leak v minus e leak. This will be set to 0. Now, there is only one term with the w. So, if we take it to the other side, we will again have a solution for w as a function of v. Rearranging this, we can easily show that our w nullcline, or in this case v nullcline, along which this is v nullcline for, and the w values along the v nullcline is what is being represented here. And for more clarity, let us put a w nullcline along the in here. So, this is w nullcline, w at the w nullcline, and this is w at the v nullcline. And this would be equal to, so it will be these two terms on the numerator divided by divided by gk into v minus ek. So, and there is a negative sign for both of these terms with the g calcium and the g leak. So, if we now plot this curve on the phase plane, this is again, as you can see, is a w as a function of v. On the right hand side, we have only v, w is not there anymore. And this curve in this case turns out to be like this. It actually goes beyond here and then it comes up and goes around. The exact figures will be available to you in the reading material, and more details will also be there. So, what we find here is that there is a one intersection point in the phase plane for the w nullcline and the, so w, this, let us call this the w nullcline, this is the v nullcline. And here, to make the distinction, this is w value at w nullcline and w value at v nullcline, and this we are calling just simply w nullcline, v nullcline. So, this intersection point is an equilibrium point. And it turns out that if we simulate this system, as you will be provided codes for, if you run the system starting exactly at that point where they intersect, right to the resolution of the simulation that you are doing, then the system will continue to stay at that point and is simply the equilibrium point of the neuron. This turns out to be the resting membrane potential. This V becomes the Vm, the resting membrane potential, and this W is the little whatever W is there at rest. So, if we start the system there, it is going to stay there, which is equivalent to what we were discussing, that if you have a neuron undisturbed, then it will stay at its resting membrane potential throughout. Of course, measurement noise and other systems noise will be there, but it will be hovering around the resting membrane potential around -60, -70 millivolts, whatever the neuron's resting membrane potential is. Remember, we are looking at a reduced system. Keep on reminding yourself, we had started with V, M, H and N. We are now considering a reduced system akin to a reduced system of the Hodgkin-Huxley, but particularly in this case there are two gating variables, of which one is very fast and we have reduced that, we have taken that out, and there is only one gating variable that whose dynamics are included, which is the W variable, and we have V as another state variable. So, thinking of this in the 4 dimensions is not easy, but the phase plane analysis and the tools that we will talk about is for two-dimensional systems, and that is in itself you will gradually see is quite powerful in terms of inferring properties about the system. So, with this equilibrium point, now if we start to consider perturbation of the system from the starting point, that is, let us say we have this as our v axis, this as our w axis. If we, let us say we have the null clines, the v null cline here and the w null cline here, somewhat like this, and this is our v rest. If we can manage to start the system slightly away from here, let us say somehow by some perturbation we move the system to the right, that is, we change the membrane potential from V rest to a different value momentarily, that is just for a brief period of time, like an instant, and this is the now the initial point. So, W let us say is unchanged and V is here. Now, we want to see which way the trajectory goes from this initial value. So, you can do the simulations yourself and you will see now to actually guide us a little bit. Let us think of this being the W null cline and this being the V null cline. Trajectories must cross vertically here and horizontally all along the W null cline. So, here the trajectory, if you simulate it, you will see that it goes up, it crosses it horizontally, then it comes down vertically and ends up here. We will, so this is the trajectory, meaning this is the relationship of Vt and Wt by starting the system at this particular voltage. So, there is a corresponding plot for just V and W over time. So, and that let us say if this is the initial V that we are starting, where this is our V rest, this is time, then we can the trajectory just simply means that the voltage increases a little bit in this direction, as you can see up to here, then the voltage reduces and goes down and then stays there, and then there is slight increase back to the resting membrane potential. So, if this is the V rest, what we are seeing is simply something like this. So, it goes below the V rest, as you can see the curve has gone below V rest, and then it comes back to the resting membrane potential. Similarly, you can have a plot for the W, whichever way it is changing. Our interest at this point is to see how the V is changing. And if you keep on moving the V to the starting V to the right, you will see that up to a certain value of membrane potential, starting membrane potential, the system goes slightly higher value and then goes back and reduces and then comes back to the equilibrium point. So, be somewhere between minus 14 and minus 13 millivolts here. In this case, it is the resting is minus 60. You will find that slightly, if you go slightly above that value, then the system goes in this direction. It's difficult to draw in that manner. You will have the exact plots, and this comes back down and here. And if you start anywhere beyond it, it does a similar kind of trajectory back here. So, that is here up to one point it is going to do this behavior, and then after that point, if this is V rest, after this particular point the increase and then decrease. So, the point here is that with a very small change in the initial condition for the V, there is a very large change in the output of the system or the behavior of the system. This kind of behavior cannot be seen in any linear systems. So, this sensitivity to initial conditions is one of the important properties of this kind of nonlinear systems, and the small change and then there is a increase in the membrane potential to a larger extent and then coming back down and going to the resting membrane potential is what in this case what we will call as an action potential or the spike. So, again we must remind ourselves that this is a two-dimensional system, a reduced version, and this carries the slower or this contains the slower gating variable as one of the state variables. The fastest gating variable, which is M for the calcium channels, voltage gated calcium channels in this case, are is the kinetics of that is gone. That is, we are assuming that dm dt is not there, M is instantaneously changing to M infinity V. And if you recall from our earlier discussion, we must remember that when we simulate these systems with the assumptions, with the different kinds of assumptions, when we reduce the system and simulate them, then the assumptions need to be appropriate in order to understand the behavior that we want to see. So, in this case M not being there, or rather the dm dt not being there, we will not be able to see the very fast phenomena called a threshold. We are seeing something close to a threshold here, that is in between these 2 points. Below that point there is a different behavior, and above that point there is another different behavior. However, we will not call this a true threshold. You will, if you simulate the system and go close by into that in between those 2 points, which we are thinking that they are the limits of the 2 different kinds of behaviors on the 2 sides. As we go in there with finer and finer resolution, we will see a gradual change in the behavior of the system, unlike what a true threshold should have. So, we have a behavior like a threshold here, that is, if the voltage is just above that value, then there is an action potential, that is the voltage increases and then drops back down to a large extent very fast, and below that it does not produce that behavior. But for a true threshold, it should be such that there is, if we go infinitesimally to the other side, to the left side or the right side, we will keep on getting the exact 2 different behaviors. So, that would be a true threshold, and in order to have that true threshold behavior, we must have the kinetics of M, and which is missing here. So, this is one of the properties of these kind of nonlinear systems. Similarly, we have another property of nonlinear systems, which is again going into oscillations, which we will start to discuss in our next class. Thank you.